All right, so welcome back, Math 211. This is now the Thursday of week 9, so I guess it's lecture number 18, I think. And we are going to start by going over the quiz. So I'm going to do this on my iPad. Let me join up. Okay. Okay, so the quiz. It says, question number 1. Garrett has the following homework grades: 8, 10, 9, 1, and 7. Show how to compute his mean score. I mean, the mean is, well, what is it, guys? You should hopefully have internalized this. How do you calculate the mean of a certain number of scores?
Add them all up, and then you divide by the number of scores, 2, 4, 5, by 5.
Add them up, divide by 5, 10, 18, 27, 20, 35 over 5, and you get an average score of 7. Number 2. After scrambling to pick up pieces of candy from a piñata, 4 children have 15, 17, 10, and 10 pieces. In parts A to C below, you should not use the formula for the mean. That is, don't just add and divide by how many. A, describe how to illustrate that the mean is 13 pieces using the idea of equal distribution. So how do I do it? Using the idea of equal distribution.
You can combine all the candy from all the kids and then go around and each kid picks one candy.
Okay, so conceptually, you lump them all together into a group and hand out one at a time, one at a time, one at a time, one at a time until you're all done. Hopefully there's no leftovers. And if you do that, you get 13 each. Of course, how do I know it's 13 each? Because, well, you kind of add them all up and it's a multiple of 13. So behind the scenes, you're certainly using some basic math, but just conceptually, you put them all into a pile and you hand them out one at a time in groups of 4, and you end up with 13 each. I was looking for a word answer there, so I'm not going to write it out, but that was the idea for the first one, the idea of a redistribution of wealth. For part B, this one, the idea of leveling out. So how do I do it with the idea of leveling out?
Make a histogram.
It's not, I know what you're saying. It's not technically a histogram. Actually, it would be better than a histogram would be a what?
Like a bar graph.
Even better than a bar graph would be what?
A dot plot.
A dot plot. 1, 2.
Wait, we had to draw?
Or just describe how you'll be doing it.
Oh, okay, cool. I didn't draw any.
Yeah, if you describe it, that's fine too. But 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's go ahead and make another one that's 10. So duplicate it. That's another 10. And then let's duplicate that again. And that's 10, but we want 5 more. And then let's duplicate that and get 2 more. So we have 10, 10, 15, and 17. And the idea of redistribution of wealth is an idea of that goes there and that goes there. Well, no, that's maybe the best way of doing it. Let's see, how shall we do this? Let's take one from the top to that pile and the top to that pile. See, even this, it's kind of hard to do it diagrammatically. So really the best way would just to explain in words what you're doing. But essentially, this is what you're doing. You're leveling them out. You're taking from the top and making them even. So maybe better to do cross out this one, and then we have that, and cross out that one, and then we have that, and cross out, and cross out, and cross out, and cross out. And you see that by redistributing the wealth, or sorry, by leveling out, everyone ends up at the same number, which is 13. If you describe in words what you were doing, totally fine, 100% fine. And because even here, like if you're in front of me doing it and I see all those cross outs, I know where they came from. But if I just see this picture, kind of hard to know exactly where it came from. So wording it would be best. And then number C, describe how to illustrate the mean of 13 pieces using the idea of a balance point. So in that case, what would you do for the idea of the balance point method?
Number line.
Number line. And then what numbers would I put on the number line?
10, 11, 12, 13, 14, 15, 16, 17.
10, 11, 12, 13, 14, 15, 16, 17. Don't got to go any further. What do I do
And
now?
there's 2 dots on 10, 1 on 15, and 1 on 17.
1 on 15, 1 on 17. And then what do I do now?
Get the distance to meet up in the middle, which is 13.
Yeah, so let's take a look. So if this one goes 1 and 1 and 1 and another 1. So now they're at 11, 11, 15, and 15. 1 and 1, 1 and 1. Now they're at 12, 12, 14, 14, 1 and 1, 1 and 1, and now they're both at 13. So again, in words, totally fine. But the idea is that by a balance point method, we end up, everything's at 13, that's the mean. So just 3 different ways of really explaining geometrically or just conceptually why the mean is what it is. Question 3, 14 women and 6 men are in an elevator. The mean weight of the women is 135 pounds, 135 pounds per woman on average. We'll say W bar equals 135 pounds. The average weight of the women, is 135 pounds. And the mean weight of the men is 193 pounds. The average weight of the men is 193 pounds. What is the mean weight of all the people in the elevator? So you can't just average 135 and 193. Why can you not average 135 and 193? I mean, I guess technically you can average them, it just won't give you anything. Why? What's the reason?
There are more women than men.
There are more women than men, so we expect the weighting to be kind of lean more in that direction. So the overall average, I don't even know, X bar. What do we do with the 135 and the 193? When you multiply 135 times 14, because there's 14 women. We multiply the 193 times 6 because there's 6 men. We add them together and then we divide by the total number, which is 20. And I don't know offhand what that number is, but whatever that number is will be the answer. And question number 4. This is very similar to number 3. A student took 15 units in the fall, 15 units, and earned a 3.1 GPA. In spring, he took 13 units and earned a 3.7 GPA. What is his GPA? So you kind of look at these two numbers, 3.1 and 3.7, and if you would just straight up average them, it would be a 35. But unfortunately, you took more units, not unfortunately, but you took more units in the fall than the spring by a little bit amount. So it should lean a little more towards your fall grade, and therefore it should be a little less than 3.5. How do we get it exactly? The same way as the last one. 3.1 times 15, 3.7 times 13, and then we add them up and divide by the total number, which is 28. And whatever number you get, you get. Any questions on that? That was the quiz. Make sense?
Yes.
Okay. Anyone unsure about any of that? Or anything else from anything else that we've done? Okay.
I don't have a question on the quiz, but are you giving us another quiz this weekend on chapter 14?
Yeah, I really should. I mean, I was thinking about it. Yeah, because we need to get more quizzes in. We've only had like 4 or 5 of them so far. We're supposed to have like 8 or 9 by now. So yeah, so there'll be a quiz let me add it to my to-do list, which is quiz on chapter 14 this weekend. Okay. Any other questions or things that you want to go over before we begin today's lesson?
And you'll put homework 14 solutions up before that?
I will put, okay, put up 14 solutions.
Thank you.
Hey. Okay. Anything else? No? Okay. Anything else I forgot to do or I should do? Okay. In that case, let me close this up and meeting. Okay. And let's load up the next chapter. We're starting a new topic now. And that is something really different. So let's everyone please open up chapter 15. And we are going to begin the chapter on analyzing bivariate quantitative relationships via scatter plots and correlation. Say that 10 times fast. I challenge you. So let's share my screen and let's go. Analyzing bivariate quantitative relationships, scatter plots, and correlation. So first, notice the difference between everything that we've done so far and what we're about to do. Everything that we've done so far in terms of means and medians and standard deviations and quartiles and frequencies and all that stuff was looking at one variable: height, weight, number of siblings, GPA, I don't know, whatever you want to think of. Everything that we've done so far is just looking at one variable. And we calculated lots of things. And if it came from a normal distribution, we were able to calculate the probability that we get a certain result. Everything's lots of fun. What we're doing now is something that's, I think, more important from a statistical perspective, which is connecting two different variables together and seeing if one has any relationship to the other. That relationship in statistics is called correlation. So here we have an example of a real life study done in 2010 of a group of young women in Muslim majority countries. On the horizontal axis, we have the years of schooling that girls can expect to receive in those countries. And on the vertical axis is the projected total fertility rate, which is how many children per woman they expect to have, or they do have during their lifetime. And when you look at this plot here, do all the data points fall exactly perfectly on a straight line?
No.
No. However, if you kind of loosen your restrictions to a perfect line and talk more about a general relationship, would you say that the relationship for the most part is fairly linear in the sense that the data points kind of cluster around the line?
Yeah.
So in statistics, when we talk about whether or not there's a linear relationship, we don't talk about whether or not it falls on a line versus does not fall on a line. But we talk about whether or not it has an overall linear relationship and how close to a linear relationship it has. We can actually quantify and give a precise number for how close to a linear relationship a collection of data actually does have, which we'll get to. That's called the correlation. It's not just an idea, it's actually a number. But for now, this is called a scatter plot because the plots, the points are sort of scattered all over the place. They're not at random because each data point represents something. In this case, what does each point physically represent?
Country.
A country. Each point is a country, not a number, but rather a country. However, each of those countries on this plot has two numbers associated with it. The years of schooling on the horizontal axis and the fertility rates on the vertical axis. So for example, which of these countries has the fewest years of schooling that girls can expect to receive? Which of these countries has the lowest number, the fewest years of schooling that a girl can expect to receive?
Is it
I'm gonna
Sudan?
say
Well, it looks like
It's
there's
going
a,
to be Chad, Sudan, and
yeah, I see actually 4, Sudan and Djibouti, as well as Chad
Niger.
and Niger. Niger? Is it? I thought it was Nigeria. Is there like 2 countries, Niger and also Nigeria, or am I just showcasing my ignorance?
there is, I don't know.
I don't know either, but we'll just go with it. So it looks like there's four different countries. So maybe that question was not a great question. Let's revise it. Which country has the highest fertility rate? Because that one only has 1. Which one has the highest fertility rate? Niger. And what is the years of schooling the girls can expect to receive for Niger? At least as far as our approximation goes.
about 4.
It looks like about 4. It looks like about 4. Does it seem that there is a relationship in the sense that women in countries with fewer years of schooling on the average have a higher fertility rate? Does that seem like a reasonable relationship?
Yeah, compared to women who have schooling, more years of schooling, yeah.
Yeah. Now, is that a causal relationship? Does one cause the other, or is that just a relationship that has things going on behind the scenes that might give a connection between them?
Behind the scenes makes a connection.
Very possibly, very probably, in fact, almost certainly. But just be aware that in statistics, we never talk about causation. We don't talk about whether or not one variable causes another. We only talk about correlation, whether there's a relationship, a connection between 2 variables. For example, it's a known statistical fact that people who own more cars tend to live longer than people who own fewer cars. This is a statistical fact. On the average, people who own more cars tend to live longer. Does that mean that if you want to live longer, you should go out and buy more cars?
No.
Well, it doesn't seem like it should, but yet nevertheless, there's a statistical fact that people who own more cars tend to live longer. So if the very act of owning more cars does not make them live longer, then there should be a connection between those 2 variables that's going on behind the scenes. And what might it be? Why do you think people who own more cars tend to live longer?
They have more money.
And what does more money get them?
They have more chance for health care.
They have more chance for healthcare. They have better access to medicine, right? They just have maybe just an easier life in general in terms of stress and how hard they work. There could be many reasons why owning more cars and therefore having more money tends to extend their life. So it's not that the very act of owning cars does it, but rather there's a connection between them. So in statistics, we don't talk about causality. We don't talk about one causing another. We do talk about whether there's a relationship between them. In this case, it's likely not just the years of schooling that is the only reason why this relationship exists, but rather other factors are playing a role without going too deeply into what they might be. So this relationship between them is linear, even though they don't fall on a line. It's not perfectly linear. In fact, if you had to give it one of three characteristics, strongly linear, moderately linear, or weakly linear, which would you off the cuff say? Do you think it's strongly linear, moderately linear, or weakly linear?
Moderate.
Yeah, somewhere in the moderate range certainly seems right. But then again, sometimes looks can be deceiving, which is why it's good that we have a mathematical value that we can assign that will actually definitively tell us what. But it certainly looks moderately linear. Is it positive or negative in the sense that does the line go up or does the line go down?
Negative.
It's negative. So we have a moderately linear negative graph. So that's three things: linear or nonlinear, strong, moderate, or weak, positive or negative. And the fourth characteristic of a scatter plot that we focus on, besides the overall form, whether or not it's how strong it is and whether or not it's positive or negative, is whether or not there's any outliers. Are there any points in our scatter plot that are so far outside of the norm that we might start to question why they're there and perhaps actually spend time devising a reason why they don't follow the overall pattern? Do we see anything here that's like, wait, why is this guy there? Anything that severely stands out?
It doesn't
No.
stand out too much, but the Palestinian just a little bit, but it's still kind of correlates.
Yeah, the Palestinian territories are slightly more off the line than the rest, but I don't know if I'd go so far as to say that it's far enough out that makes us truly question it. But then again, luckily there's math that can help, various formulas and whatnot. But when I look at it, I don't see anything that severely lends itself to being an outlier. Okay, so the word linear, as I said, has a different meaning in statistics than in algebra. In an algebra, linear means they lie on a line. It's got to be a perfect line. Whereas in statistics, as long as they cluster around a line, it's good enough. Now, in this graph, I certainly see this guy down here, and I would venture to say that this one at the bottom is an outlier. Whereas this one here, not so much. It's still basically along the right pattern. It's slightly off the beaten path, but not nearly as much as this. Make sense so far?
Yep.
Yes.
Yeah.
Okay. So now just be aware that when it comes to doing math with statistics and scatter plots, we can do really good math with linear relationships, but we don't have an easy time with nonlinear relationships. And when it's not linear, there are tools, more advanced tools that you can do that we're not going to worry about. As far as we're concerned, the only ones that exist are linear relationships. If it's not linear, the most you got to do is recognize that it's not linear. So here we have a scatter plot. On the horizontal axis, we see 2013 GDP per capita, some economical term involving the economic strength of a country. And on the vertical axis is a ladder of life from 0 to 10. Which step do you stand at the present time? In other words, if I asked you right now, like, where are you in the ladder of life? You might say, a 3 or a 4. You're in college, you haven't gotten a full-time job, you don't have a family, you don't have a house. There's various things that you might see as the passage through life, and where are you on that ladder? You might give a lower number. So people in different countries might give different responses, and what we're looking for here is the percent of people saying that they are somewhere between 7 and 10. And if you ignore this curve here, which they kind of threw in, it doesn't, you might think it's linear. It certainly seems like it's like this. But again, it's not necessarily obvious that data is linear sometimes just by looking. And this particular scatter plot seems to indicate that it's actually has this curve that once you reach a certain point, it kind of levels off. In general, though, the further you go to the right, the higher the GDP per capita. What is the relationship? The further you go to the right versus the percent saying that there's somewhere between 7 and 10. Would you say it's going up or going down?
It's going up.
It seems to be going up. Certainly seems to be going up. Perhaps linear, perhaps not linear. But it certainly is a positive relationship. Okay. Why do you think, it asks, that the relationship flattens out as GDP per person increases? Why does it not continue going up and up and up forever? And this is not so much a statistics reason as it is a common sense reason. And not everyone's common sense is equal. Myself, I'm not even sure, to be honest, why it kind of flattens out. I don't know, maybe, I don't even know. What do you guys think? Anyone have an idea? Any sociology or psychology majors here who might have an idea as to why, why it tends to flatten out? Nobody, huh?
Maybe people get spoiled. It's like there's a culture where everybody's like rich. You take for granted stuff that people in like an emerging market, which are a lot of the high yellow dots, are appreciative of.
That could very well be. Maybe, we certainly, what's that phrase called? First world problems. My cell phone doesn't have reception. My life's over. When you have countries around the world that don't even know what a cell phone is or have no access to one. So perhaps we are somewhat spoiled, and therefore, I don't know. Could very well be. I don't have an answer for this. I don't want to spend time on it because I don't like spending time on things that I don't know. So we're going to move forward. Anyways, strength and trends. Okay, so linear relationships can be classified as strong, moderate, weak, or even none. There's no set rules for this. I've looked around on the internet, and different math books and websites give different cutoffs for where the transition is from strong to moderate, or from moderate to weak, or from weak to none. There's no hard and fast rule anywhere. It's not like, in the Bible when God said, let strong relationships have this property, right? These are things that we've devised, and therefore the definitions for the cutoffs are our own. Certainly the top left one is not only strongly linear, it's more than strong, it's perfectly linear. You can't get any more linear than actually falling on a line. That's about as strong as it gets. That is as strong as it gets. Which of the other graphs there, amongst the other 5 scatter plots, would you say is the next strongest after the top left?
Bottom right.
Bottom right looks very strong. Which one after that would you say?
The bottom left.
Bottom left, and next.
The bottom middle.
Bottom middle, next.
Top middle.
Top middle, and then finally the top right. In fact, the top right is so nonlinear that if I asked you to draw a line through them that best fits the data, I don't even know what direction to make that line. See, strong, there's no question where the line is, or at least approximately. Even moderate, there's not really any question. But when you get to weak, you can kind of spot a weak scatter plot by struggling to fit a line to it. The top right is so nonlinear, I wouldn't even venture to guess what the line might be. Does that make sense? So the top left is perfectly linear. The bottom right is strongly linear. I would say the bottom left and the bottom middle are moderate. The top middle is weak, and the top right is none. That'll be my off the cuff guesses. Does that make sense what I'm saying?
Yeah.
Yeah, okay. Hershey Park in Pennsylvania contains some of the most famous roller coasters in the eastern United States. This scatter plot shows the relationship between the track length and the ride time for 11 roller coasters. As the track length goes up, you would think that the time should also go up. But it doesn't really seem to have that pattern, does it? It says circle the dot that represents the roller coaster that you think is the most terrifying ride. Which dot represents the most terrifying ride here?
The one that's at the bottom but far right.
One that's at the bottom and far right. So you're saying that this one is the most terrifying?
Yeah.
I don't know. Well, tell me why. It's
because we'd be going incredibly fast to go through that track length in that amount of time.
Yeah, that's pretty good. It has an incredibly long length compared to everything else. It's the longest and shortest. Longest lengthwise and shortest time, which means you have the fastest speeds. Does everyone see that? Everyone agree?
Yeah.
Yeah, that's probably the most terrifying, all else being equal. Yeah. What's the track? Yeah, go ahead.
Wouldn't it be the ride time? The right time is how fast it's going?
Right, yeah, the right time is how fast it's going. Okay.
So wouldn't the top point be the fastest?
This one here?
Yeah.
Well, this one here takes 3 minutes to go.
Oh, it's a total time. It's not like the miles per hour.
No, that's a total time. That's the ride time. Right? So that one takes, you have 3 minutes to go a lot less distance than this one does. This one in a minute goes further than the other one does, right? So in 1/3 the time, it's going almost twice as far.
Okay, got it.
That makes sense what I'm saying, right? Yeah?
Yeah. Yes, yeah.
All right. So what is the track length for Skyrush? It seems to be about 3,900 feet. What is the ride time? Seems to be about 65 seconds, give or take. Summarize the relationship between track length and ride time. What's the overall relationship between track length and ride time?
Speed?
Well, when you say relationship, we mean, is it linear? Is it nonlinear? If it is it strong? Is it moderate? Is it weak? Is it positive? Is it negative? Are there any outliers?
It's really weak. It's all over the place, right?
Yeah, it's really weak. I mean, I don't really see a really, luckily, oh, I don't even have the numbers, so I can't even do it on my calculator. And we haven't learned how to do them yet. So yeah, I mean, if these guys up here weren't here, how do I do this? If these guys weren't here, I'd have a very strong, not as strong, but I have a pretty moderate relationship like that. But with those guys there, it's hard to see anything. Yeah, I would still say something like, how do I do this? I would still say maybe something like this summarizes the data. It's a very, very weak linear, but I do see a downward trend overall. But there's a couple guys here that really make it difficult. As you can see, this is not, I mean, sometimes like in the previous page, some of these are very easy to tell. This one up here, this one here, this one here, even to this one. But sometimes it's not so easy to tell what the relationship is. You shouldn't have any where you have that kind of confusion, where it's difficult to determine what it is. Like here, this one's much better. To study the factors that affect student success, CSUN conducted a study of the high schools that send 25 or more students to CSUN per year. For these high schools, is there a relationship between the average SAT verbal scores of entering CSUN students and the percentage who get a grant or scholarship? So here we have a plot. And they actually were very nice. They actually drew a line through it that they claim is the summary line or the best line for the data. Would you say that this relationship is linear?
Yes.
Okay. What about positive or negative?
Negative.
Negative, strong, moderate, or weak?
Strong.
Seems fairly strong. In fact, as we're going to see later, you'll notice that there is a number down here, r squared equals 0.822. A general rule of thumb is that if r squared is 0.7 or above, it's considered strong. That's a general rule. So if r squared is 0.7 or above, it's considered strong, and 0.822 falls in that category. But again, there's no hard and fast rule for this. Different websites give different cutoffs. But 0.822 is certainly fairly strong. So more students come from Granada Hills than any other high school. In fact, 41.1% of Granada Hills students get grants or scholarships. And their mean SATV score is 491. Circle GH on the scatter plot. Which of these diamonds represents Granada Hills? Anyone?
I would say the one that's like directly touching the line.
This one?
No.
No, more to the left.
This one?
No, down.
This
On
one?
the line, yeah.
I would
Yeah.
say that one.
This one down here? Well, let's see. If I draw a line from it directly left, and I draw a line from it directly down, do those seem to be 491 and 41.1% respectively?
Yep.
Looks good to me. Looks good to me. Okay, excellent. Circle the term that best describes the relationship. Is it linear, curved, or neither? I already answered these, but let's just do it formally. Linear, curved, or neither?
Linear.
Linear. Are there any outliers?
No.
Doesn't look like it. Increasing positive / decreasing negative, or neither?
Decreasing negative.
Decreasing. And is it strong, moderate, or weak? Or maybe it varies, so like it's strong in one place and moderate somewhere else?
Strong.
Looks fairly strong to me. R squared 0.822. Does that make sense so far?
Yeah.
Okay. So now let's talk about this number, this correlation. R squared, by the way, is not the correlation, but it's connected to the correlation. The correlation is not R squared. The correlation is R. R is the correlation. And we're not going to give the formula for it, but I will say it's always between -1 and 1. So if you have a relationship that's perfectly linear, falls on a straight, perfect line, the correlation is 1 or -1. How would I know if it's 1 or -1? What should give it away? What do you think the difference between a perfect line 1 and a perfect line -1 should be?
Whether it's going, the line is going decreasing or increasing.
Excellent. If the line is increasing, we use R equals 1. Well, we don't use, I mean, the number is R equals 1. And if it's decreasing, it's -1. In fact, anytime it's going up, it's positive, and anytime it's going down, it's negative. So 0 is the worst. 0 is the blob of points that has no linearity whatsoever. The closer it is to 1 or -1, the stronger is the correlation. So this one here, ice cream consumption. As the temperature of the day goes up, the amount of ice cream per person eaten also goes up. Seems reasonable. People like ice cream on a hot day. Which of these numbers do you think best represents the value of R? So first, which ones can I throw out as being impossible?
0.
Right? 0 we're going to throw out because 0 indicates a blob of points with no linearity whatsoever. And I certainly see a linear trend here. What else could I throw out?
The negatives.
The negatives, because the negatives indicate a downward trend. And here we certainly have an upward trend. So we're left with 0.2 or 0.9. 0.2 being fairly close to 0 and 0.9 being fairly close to 1. So of the two, which one do you think is the more likely answer?
0.20.
Well, 0.20 would indicate that it's extremely close to being nonlinear. In fact, 0.20 is extremely weak, if even non-existent. Whereas 0.9 is very strong. Because if R is 0.9, what is R squared? What's 0.9 squared?
0.81.
0.81. And we know that R squared greater than 0.7 is strong. So R is 0.9 is strong, and 0.2 squared is what? What's 0.2 squared?
0.4.
Not 0.4.
0.40.
Not, that's the same as 0.4. 0.4 and 0.40 are equal. What's 0.2 squared?
0.04.
0.04. Numbers that are smaller than 1, they're between 0 and 1. When you square them, they get smaller. 0.2 squared is 0.04, which is extremely weak to the point that I wouldn't even see a line. So I ask again, do you think this is strong or weak? 0.2, 0.9, or 0.2?
0.9.
0.9. This is a strong relationship. Does that make sense so far?
Yeah.
Yes.
Yeah. Okay. In fact, let's go one step further. We have 5 plots here. Let's guess, not guess, but let's make an educated guess as to which number corresponds to which plot. Let's start with the 0.95, which is a very strong positive linear plot. Which of these would be a very strong positive linear plot?
You mean negative?
E.
C. And C, right? C is extremely strong positive linear. Do we agree?
Yep.
Yeah. Okay. How about the negative 0.95? Which of these is a very strong negative linear plot?
E.
E. We agree with that? Very strong negatively linear? That's a horrible line, but yes, do we agree?
Yes.
Yeah.
Okay. Now, one of these is a 0. Which of these is a 0? Remember what a 0 is. A 0 is basically a blob of points with no discernible pattern.
E.
E.
That's certainly going to be D. And that leaves us with the 0.5 and negative 0.5, which are going to give us moderate to weak positive and negative graphs. Which of those two is the positive? Which of those two is the negative?
B is positive and A is negative.
B is positive and A is negative, right? If you had to make a line for these, this one would look something like this, and this would look something like that. Do we agree? I'm not even drawing a line through this because there's no line. I mean, there's no line that stands out. Yes? No? Maybe so?
Yep.
Okay.
Yes.
So the next question is, how do we actually go ahead and compute the correlation R? It's nice that they give us R. It's fantastic we can guess R, but how do I actually compute R? An Algebra 1 Common Core standard is to compute using technology and to interpret the correlation coefficient of a linear fit. So here we have an example. It says circle the correlation between arm span and height for these 8 students. In general, as people get taller, would you expect that their arm span to increase or decrease?
Increase.
Increase, right? Taller people will probably have a wider arm span. If you were to draw a line through this data that best fits the data, would it be a positive line or a negative line?
Positive.
It's positive. Something like this seems fairly reasonable, not necessarily perfect, but ballpark.
Yeah.
Okay, so which of these possible correlations can we throw out as being impossible? Let's go left to right and throw out the ones that we know can't be.
All the negatives.
All the negatives are out.
0 is out.
Zero's out. One other one of these is out.
1.
One's out because it's not a perfect line. And then we have 0.24, which would be a very weak, 0.53, which would be a moderate, and 0.93, which would be strong. And at that point, it's kind of hard to tell. I would certainly, my guess would be moderates, but I could be wrong because when you do it by eye, it's very, very difficult. So what I'm going to do is I'm going to do it on my TI-84 calculator. Now, who here has a TI-84 calculator?
I do.
I do, but it's dead still.
Oh. Well, for those of you who have a TI-84 calculator, here's what I want you to do. I want you to take it out. Now, I only mean those where it's not dead. If it's dead, you'll have to continue mourning for a little bit. But I want you to hit the stat button right in the middle of your calculator, stat. And you hit the stat button, you'll see something that looks like this. And I want you to hit enter. I want you to edit. And what we're going to do is we're going to put in some data. In the first column, which I just deleted, we're going to put in all of the first entries, 161, 196, 177, 188, 159, 178, 194, and 188. So the first column of data, list 1, L1, I just put it all in there. Now I'm going to go to list 2. And I'll put all that data in there. So my computer's about to die. I have to go get a charger before it does die. Please go ahead and put those lists in. I'll be back in just 1 second. Okay. Oh, okay. Oh.
Oh, cool. Oh, that's awesome. Yeah. Wow, I love that. Thank you. Thank you so much. Very nice. That's rad. Okay. And then it's gonna hang and people are gonna like, it's kind of gonna be where like the photos. Yeah. Yeah. Fabulous. Thank you so much. Yes, of course. Get it done. Thanks for that.
Okay, I'm back. Okay. Did everyone, did anyone have a chance to do it? Put in those data?
Yeah.
Okay. So what you do now is hit the stat button again. This time, go to the right to calc, and then go down to the fourth one, linreg AX plus B. And when you do that, you should have something that looks like this. X list should be L1, Y list should be L2, and frequently list should be blank. And then you go down to calculate. And when you calculate, what do you see? What's the R value?
It is 0.9308541.9.
0.93, which means that my initial guess as 0.53 was wrong, which just shows that it's hard to do it by hand. And then Elizabeth was so sweet. She did an online version. I should have even thought about that because they're all over the place. An online version. Do a Google search for a scatter plot correlation calculator or something, or just click on that button there. And you should be able to plug all the data in and got the same answer. So 0.93 is the thing. Now, interpret the value of R in context. Interpret the value of R in context. And that's a very strange question because R squared actually has a very important physical interpretation, whereas R itself doesn't. There's nothing physical about R, but there is about R squared. Yes, so what I'm going to do is I'm going to give you the R squared interpretation and not the R interpretation. So what is R squared? Well, by the way, the same button on your calculator that gave you R also gave you R squared. In this case, what is my R squared value?
0.866, and then it keeps going.
All right, we'll say about a 0.866. And the question is, what does that R squared equals 0.866 mean? So look at all of these data points. Each one has an X value and also has a Y value, correct? Right? Every data point has a height and an arm span, correct? X and Y, although I put them in backwards, but that's okay. I mean, I didn't put them in backwards. Well, I did put them backwards. The PowerPoint should have them reversed. X should go in list 1 and Y should go in list 2. What's amazing about the correlation, it doesn't care which list is which. It correlates. So whether you do X1, Y1 or X and Y switch, it gives you the same answer. But anyways, if you look at all of these points, do they all have the same arm spans? Are their Y values all the same, all those points? You can just answer this by looking. Are the Y values all the same?
No.
No. What are 2 reasons why not everybody has the same arm span?
Because not everybody is the same height.
That's a great reason. That's an amazing reason. Not everyone has the same X value, right? Look at people who are taller. The whole idea is that taller people should have a bigger arm span. You change the X value, it's expected to change the Y value. It's a great reason. But look at these 2 guys or girls. I'm not sure who they are, but those 2 people. They have the same X value, and yet even so, they have different Y values, which means height can't be the only reason that arm span changes because they have the same height, but different arm spans. So what are something else besides arm spans, besides height, that might influence arm spans? Because height can't be the only answer. If it was, what was it?
Genetics.
Genetics. That's a pretty good reason. I mean, that's just life.
Nutrition?
Genes, right?
Nutrition also?
Nutrition, sure. I mean, if someone's growth is stunted somehow, would that also stunt their arm span? I don't know how these things work, but certainly genetics should be a factor, correct? So the R squared value tells you how much of the reason that the Y values change can be explained due to height changing, due to the X value changing, versus every other thing that you're not thinking of. 86.6% of the reason why the Y values change is because the X values are changing. And the other 13.4% are all the other things that we're not thinking of in this study. So genetics, nurture, and all the other things that might play a role, that's all lumped into the remaining 13.4%. The R-squared value tells you the percentage of the variation in the Y values that can be explained because of variation in the X values. The other explanations, that's all lumped into the remaining 13.4%. That is the physical interpretation of R squared. Does that make sense?
Yes.
Okay, I hope so. It's a little subtle, and historically, people in stats classes have a difficult time with that one. So no one is asking. I'm hoping everything's okay. So correlation and the units of measurements. Convert the missing measurements to inches. So the idea of this one is as follows. If you change anything, change from height in centimeters and arm span in centimeters to height and arm span in inches, the question is, will the correlation change? And the answer is no. Correlation doesn't care about units. If you change the units, correlation stays the same. Centimeters to centimeters, inches to inches, inches to centimeters, centimeters to inches. We'll get the same thing in all four cases. Correlation does not change. In fact, look at these scatter plots. What do you notice about these four scatter plots?
They're all the same.
They're all the same. And because they're all the same, even though the scales are different, but because they're all the same, it turns out that we get the same scatter plot and therefore the same correlation. Correlation does not depend upon units, and it does not depend on switching X and Y. You get the same results. In fact, this is what the next one says. If you switch X and Y, what happens? The correlation stays the same. The connection between them does not change if you switch the order that you're connecting them in. Okay? The next question is about outliers. In a scatter plot, there are three types of outliers. It can be for one variable, but not the other. Or it can be for both variables. Or it can be not an outlier for either, but is an outlier when we consider them jointly. Now, that one's a little tough to wrap your head around. It's really certainly best seen in an example. So the scatter plot on the next page gives the weight in pounds and length in inches of a large sample of black bears. For each point, A to E, tell which type of outlier it is, and then describe the bear. Okay, so here we have a scatter plot of a large number of black bears where we have length in inches on the horizontal axis and weight in pounds on the vertical axis. And they gave us 5 points, A, B, C, D, and E. And they say these fall into one of three categories. Either an outlier for one variable, but not the other, an outlier for both variables, and not an outlier for either unless you consider them together. So let's look at A first. Is A an outlier when it comes only to length in inches? If we don't consider the Y variable, but only focus on length, is the length of A outside of the length of all the others in our study?
No.
No, it's 53 inches, which is lots of them are around there. I mean, the lengths are all over the place. So this length is a perfectly valid length. Nothing's an outlier about the length. Is it an outlier when it comes to weight? Is its weight
Yes.
Well, why? All these guys have the same weight and they're not outliers.
Oh, okay.
Right? When it comes to weight, it's no different than all these ones, isn't it?
Yeah, you're right.
right? So its length is perfectly fine. Its weight is perfectly fine. But only when we consider length and weight together do we say, wait a second, this one does not fit the pattern. So it's not an outlier for either variable, but it is when you think of them together. Does that make sense? Yes?
Yeah.
Yeah, so you would say they are jointly, it's a jointly.
It's a joint outlier. It's an outlier only when we consider both variables together. Now look at B, for example. Is B's length an outlier? Just its length alone. Is its length outside the trend, the normal part, the collection?
No.
No, lots of them have the same length. Is it an outlier when it comes to weight?
Yes.
Yes. Okay, all the weights are from here to here. And then we got a big gap until its weight. So it is an outlier when it comes to weight, but not an outlier when it comes to length. How about C? How would you describe the outlierness factor of C?
It would be an outlier of length.
It would be an outlier of length, but not width, but not weight, correct? Right? Length, it's out to the norm, but weight-wise, it's right in here. Nothing wrong with the weight-wise, correct?
Right.
Okay, and how about D?
Wait. Yeah.
Both.
Well, it's not an outlier when it comes to length. As far as its length is concerned, it's no different than these guys. And as far as weight is concerned, it's no different than these guys. Right? So it's not an outlier. It's like A, right? It's not an outlier for either separately, but it is an outlier when you consider them together. Right? Its length is the same as these. Its weight is the same as those. But when you look at length and weight together, it's out here in the middle of nowhere. Agreed?
Yeah.
Yes.
And what about E? E would be an outlier for both variables. I don't need to worry about joint. It's already an outlier. Its length is way outside the norm. Its weight is way outside the norm, even not considering the other variable. And certainly together, it's out to the norm. But it is an outlier for each variable separately. Will we agree on all that?
So there's a difference between it being an outlier for both and it being a joint outlier?
Yes. An outlier for both means it's an outlier whether you consider only length or only width. It's an outlier, but in both cases. Whereas A and D are not outliers if you consider only length or only width, but is an outlier only when you consider both of them together. Make sense?
Yeah.
Okay. And then it says, describe the bear. How would you describe bear number A? Or bear letter A, I guess makes more sense. Not really number A. That would be kind of weird. How do you describe bear A?
He's heavier than most of the bears his size.
Yes, excellent. When you look at the bears his size, he's extremely heavy in comparison. This is an overweight, short bear. Whereas D, for example, or it's going over B, for example, anyone?
Is that one also heavier?
He's also heavier than other bears his size. That's correct. Also overweight compared to the bears his size. Right? D is underweight for the bears his size. Right? C is extremely tall for the bears his weight. And E is just a very tall, overweight bear. I'm only going quick because, you know what, I'm not going to finish this anyways. There's just too much more to do. We didn't quite finish this.
What did you say C was?
C looks to be a very tall bear compared to other bears his weight.
Okay.
Right, around 400 pounds. Most bears 400 pounds. He's extremely tall in comparison. Okay, so we didn't quite finish 15. We will finish 15 on Tuesday and start 16. I will put up the homework, the solutions for 14 tonight. I will put up the homework for 15 tonight. And we will also put up the quiz for 14 for the weekends. And the test is next week. So yeah, so that's it. Any questions? Well, in that case, have a good weekend, everyone, and thank you as well. You're welcome. Thank you. That's even better. And I will see you guys Tuesday.
Later.
Have a good Halloween and stuff.
You Tuesday. Have a
Thank you,
good one.
Professor. You too.
Oh, I also listened to the music you recommended. It was very good.
You guys like every one of his songs?
I listened not to every single one, but like 2 or 3.
They're crazy good, huh?
Mm-hmm.
Crazy good. All right, good. Fall down that rabbit hole. You'll never come out again.
Bye.
All right, everyone. Bye. Okay, Catalina's here. Catalina, I did find your test for some reason. It didn't show. I had to like click on your name and it was there. So I don't know exactly what the issue was, but I did find it.
Okay, good. I don't know why it does that. It does that with the homeworks too. It just doesn't say turned in.
Really?
Well, yeah, like when I turn in my homeworks,
Yeah.
when you look on your end, you have to click my name to find the pages, and I don't know why you have to do that extra step.
That's true.
It's something with the classroom thing.
That's weird. I don't know why that's the case. But I'm just glad that, oh, I should stop recording.